Guys, let's get started. So actually first some announcements. So the good news is that there won't be any p-set we're handing out this week. So what we're going to do instead is when you get back on Monday from spring break, we're going to hand out a p-set then, and we'll have until Wednesday.
It'll probably
Not
be
that
posted,
Wednesday, the weekend.
It'll probably be posted this week on the website.
Yeah, we'll post it this week on the. So it'll be slightly longer than average, but you'll have a bit more time. That'll get us back on the Wednesday to Wednesday schedule. Now, the other announcement is I'm not going to be here on Monday after spring break. I give a talk someplace, so I hate to ruin your spring break, but I won't be teaching on Monday. And one of these fine gentlemen may or may not teach, so we'll send out an announcement, which should be a fun lecture. So let's see, I think that's it in the way of announcements. Are there other things that, yeah, so that's it. Last time we talked about the ellipsoid algorithm. So who can give me a short description of, what one of the main takeaways is from the ellipsoid algorithm? Yep.
Now we can determine if our convex viable solution, feasible solutions is not empty.
Yes, exactly. So given
He pointed the camera at me.
oh, all right.
I made a mistake.
You never know when you're going to get pranked in MIT, so I wasn't sure what that was. All right. So, one of the main takeaways from it was actually that separation. Well, actually, we did it through feasibility, but it already gives you the ability to do optimization. So if you think about linear programs, so remember separation is this question of given a point. Well, given a query, you want to figure out whether it's in the convex set. And if it's not, what you want to do is you want to find a separating hyperplane that gives you which direction you have to move in to have any hope of getting into the convex set. That's something that's utterly trivial to do for something like a linear program, because how would you build a separation oracle is you just look at it and you check. And if one of the inequalities is violated, then that is your separating hyperplane right there. So what we talked about is we use the ellipsoid algorithm as a way to go from separation to feasibility to then optimization. Now there's this catch that we talked about and a lot of people brought up is that with the ellipsoid algorithm, you're actually assuming a condition that the ellipsoid is contained, that the convex set to begin with is contained within some huge ball. And if the polytope or convex set is non-empty, it better contain some tiny ball where you don't know where that center is. So that already assumes that your convex set that you care about feasibility problems with is itself full dimensional. So it's a bit of a technicality and a headache to actually show how to deal with the case when your convex set is not full dimensional. But there's actually a way to reduce it to Farca's lemma. So I put on the course website a link to some details about how to actually do that. So you can check that out if you're unconvinced about whether the ellipsoid has really solved the full problem, but I won't tell you more about that. Instead, today what we're going to talk about is we're going to talk about a really neat application of the ellipsoid algorithm, and we're going to talk about, it'll be a relatively self-contained topic. We'll be talking about submodular functions. So these are a great example of taking a general approach to problems in combinatorial optimization, seeing that many different things you study can actually be put under the same hood and studied through what's called submodular functions, and by connecting them to actually the ellipsoid method and convexity. So that's what we're going to do today. So it should be a slightly shorter lecture than usual just to talk about submodular functions. But let me tell you what a submodular function is. And this will be the main focus. So first thing I'm going to do is I'm going to tell you what a submodular function is. I'll actually give you two equivalent definitions for them. It won't be obvious that they're equivalent, but that'll be one of the problems on the p-set is to show that. And then I'll show you some examples of submodular functions so that you can wrap your head around where these types of things actually do come up, because a great many things are actually examples of submodular functions. So what we're going to do throughout today is there's going to be, a submodular function is a function on a set. So we're going to let capital N be a set. And let's just assume, because we really care about the size of the set, that it's little n. So now we can think about a function, a general function, a set function, f, that maps some subset of capital N into a real value. And in fact, this function is submodular if the following condition holds. So I'm actually going to tell you what's the slightly less standard definition of submodular functions, because I think that's actually even easier to motivate. I'm always surprised people talk about it the other way first. Well, my favorite way to think about submodular functions is that they satisfy the following condition. If I take a set A and add in an element J into the set, and I look at how much that changes its value from what it used to be, well, that'll be at least what the value changes when we do it for a set B instead. For all different pairs of sets where A is actually contained within B, and for all different choices of which element J you want to do. So the way to think about this condition, it's actually a very intuitive condition. The way to think about this is that it's a type of...
J outside of B.
J... No, I don't think it matters, but in any case...
Oh yeah, it doesn't matter.
Yeah, so it doesn't matter, but don't worry about that. So the way to think about this is that you should think about this as diminishing returns. So imagine that you've already taken in some set A, but there's some potentially larger set B, and you look at how much the gain is of now adding J into your set. You should actually get a larger gain. This gain actually could be negative though, so you should keep that in mind, that these functions are not necessarily monothonically increasing.
Yeah, so
but
given that's likely negative, then it actually does, you actually do need to say J is not in B.
J is not in B? All right.
Yes, if J is B, it's in B the right.
It gets zeroed out.
Zero.
Ah, okay. All right, fair enough. All right, good. So it's a type of diminishing returns where, you know, how much you get as the change when you actually add J in to a set A, well, that's actually lower bounded by what happens if you had a larger set B. So this is a very natural type of constraint. There's actually an entirely equivalent version of it, which you won't see immediately why they're equivalent, but we're going to go back and forth between them. But you'll prove that they're actually equivalent. This is actually the more standard definition, is that another way to think about what a submodular function is that for any set, any pair of sets, A and B, regardless of what they are, well, you'll have the property that f of A intersect B plus f of A union B is itself upper bounded by the sum of the two values on these different sets. So this is oftentimes the standard definition for submodular functions. There's a purely equivalent version, which is through diminishing returns, which actually I find a little bit more intuitive as to why the notion of submodularity is so pervasive. So do these definitions make sense? You won't necessarily see why they're equivalent yet until you finish the P set. But let's think about what are common examples of submodular functions. So I claim you've seen some submodular functions. They're actually very natural. So let me give you a little bit of a taste of where exactly they would come up. So let's study some examples, and then we're going to study submodular functions in general. So one of the simplest examples that you can do is what's called the coverage function. And a coverage function is really describe what the function is as described by some bipartite graph, where you think about the set on the left as being your base set, and you think about an arbitrary other set on your right-hand side, and you have some bipartite graph here, so there's some edges between the right and left side, which now what you're going to do to actually how this bipartite graph is going to define a function, which is indeed submodular, is very simple. Is what we're going to do is we're going to set f of A, given some subset of the vertices n, will just be the number of neighbors of A. So all you're going to do is when you're given some set here, for example, this might be your set A, Well, you're going to look at all of the different neighbors, and in this case, when you plug in the singleton set, you're actually going to get out the value 2. But the point is that in this vantage point, it's actually pretty easy to see that this type of function has diminishing returns, because the larger your set is to begin with, when you add in a new element like j, and you talk about how many new neighbors this adds in, then the more things you started off with, the less new things you get that you cover. So this is one type of diminishing return situation, is coverage. This comes up, for example, in when you talk about like placing sensors that you want to be able to cover an entire region of space. Yep.
Does it have to be by part type?
Does it have to be by part type? Well,
I don't think so.
I don't think so, but you have to be careful about what you mean by neighbors then, so that, you know, actually adding in, you can do it, but it's a little bit easier to think about it for bipartite, I think. So let me give you another example. So actually there's a very natural example of a submodular function. Can anyone think of another example that they might have seen someplace? Okay, a little too easy. A linear function, definitely. But good one, yeah?
Log of the size of the set.
Log of the size of the set. Ah, that's good. Actually, that's a special case of the thing which I was going to say next. So that's, there's even a slightly more general one that's exactly along those lines. Yep.
The concave function of the set.
Yeah, then, so I was actually going for entropy, but that's a different way to generalize it. So one way to do it is actually entropy, which log of the size would just be a uniform distribution on something like that. But let me make it precise, which is here's at least one way to think about another one, is to think about the entropy function. So one way you can think about the entropy, it's a little bit different than in your example, is you could think about n, this base set that we're starting off with, is actually, we can think of it as a collection of random variables in some domain. And we can choose x1, x2, up to xn, so each one of them is associated with some random variable. And now what would we do is we would define f of a, of some set, to just be the joint entropy of all of the different random variables in this set A. And this also has the type of diminishing returns aspect. Now when you think about, for example, adding in one random variable to the empty set, well, you add in whatever the entropy of that random variable is, but as soon as you talk about you already have one element there to begin with, when you add in another one, you add in at most that entropy, because you might have removed some entropy already if they're dependents between these different random variables and they're not actually independent.
Wait, how are you claiming that this reproduces log of the size of the set?
The mapping is a little more involved, so let's not do it.
Yeah, so maybe that's not true.
Yeah, because this one, it's different what n is in those examples, but let's not get too sidetracked. So I want to do one more example of this, which is something you will have seen as well. This one is a little bit less clear. You might not know that it actually satisfies this property. But also the graph cut function is a very common example of a submodular function. So here, what you're given is you're given some graph G, which now n, our set system, is going to be the set of vertices. And it has some set of edges between them. And in this case, what we can do is we can define f of a to just be the number of edges crossing between these two sides. And that turns out, if you check it, to also have the submodularity property. In fact, I think it's easiest to check that it's submodular for the second property, not for the diminishing returns. So in fact, submodular functions are, they appear in many different places, so it's a very general concept. And there are actually many properties that you can think about studying for things like submodular functions. So, you know, some of the questions that you could ask, optimization questions about them, is, you know, you could ask to, for example, maximize them. You could ask to minimize them. You could even ask to do some variant of these things, either max or min, with some constraints. So you can think about something like the coverage problem. You know, if you were to represent it as nodes on the left represent different sensors that are then covering different locations that they can detect what's going on, you might have some sort of budget of the number of sensors that you can place. And in that case, you'd be trying to maximize a submodular function with some cardinality constraints over the size of the set that you want to begin with. So many of these problems, things like maximization, are hard. And people study things like approximation algorithms for them. But one of the beautiful results in this area is that actually it turns out you can minimize computationally efficiently any submodular function. And now what's interesting about this is that if you think about this function, if you think about some of your submodular functions that, many of these special cases, they're things which you could be given the description of the input. But in this case, when you're given an arbitrary submodular function, there are, you have no way of actually representing one of these things. You're only given black box access to it. So it's a very different way of thinking about interacting with this type of function. And it's a little bit magical that even though that you're given only black box access to this function where you can query it on different sets, it turns out you can still efficiently find the minimum of any submodular function. And the way we'll actually be, to doing this, we'll actually be developing an analogy with what are called convex functions and tying it to the ellipsoid method. So there's this beautiful line of work within combinatorial optimization, which is what we're going to cover today, albeit briefly, so you could take entire courses on these types of things, but we'll see just a glimpse of it. Is, our approach today is we're going to give algorithms based on the ellipsoid method for minimizing a submodular function. And actually, the way that we're going to do this is we're actually going to develop an analogy with what are called convex functions. We've talked about this a few times, but we've never precisely defined what they are. So today we'll talk about convex functions. And actually it turns out that this notion of submodularity should really be thought of as a discrete analog to convex functions. So this is what the notion of convexity should really mean in a discrete setting. So we'll develop what exactly we mean by this. Is there a question? Yep.
It's kind of a philosophical thing,
Yeah.
because you see, if you look at the definition there, it's more like a concavity thing, and you look at entropy, it's concave, because diminishing return is concave, but why is it behaving like convex here?
Lovász will answer that question in a few minutes. As in, you'll see. That's a very good question, but we'll get to it.
Okay.
That's a very good question. So that's part of what seems a little bit mysterious. Let me first define convex functions. Let me give you an idea about how the ellipsoid method actually relates to convex optimization, but this is only a sketch. And then the rest of the lecture will be designed as trying to figure out what this analogy is between submodularity and convexity. And we're actually going to see a really interesting proof technique through LP duality. So it'll be a little bit more bizarre than things we've seen. So it's cool. So all right, what is a convex function? So a function, let me call it G. And let's say it's from Rn to R. Well, it's convex if we have the following property, that for any lambda in the interval 0, 1, we take any values, x and y. Well, we better have that the convex combination of their values is an upper bound for actually G evaluated at the convex combination of the 2 points. So we want this to hold, for all x and y, and for all lambda in the interval 0, 1, right? So this, in the case of just functions on the real line, you can think about something like x squared. All this is saying is that if you take something like x squared, and that's your function G, that if you take any 2 points on the parabola and you take their average, then that line lies entirely above the parabola, because taking the average of the values is going to give you something larger, or at least as large, as G evaluated on the average of the points to begin with. So it's a very natural notion In fact, the reason these things come up for things like the ellipsoid method is just by a simple picture. So this is just designed to be a sketch, but here's the idea. So the main upshot is that these types of functions are actually easy. Convex functions can actually be minimized, and it's really important that we talk about minimize over convex sets. And let me add a little caveat in here that really what we mean is that they can be approximately minimized in the sense that you can get arbitrarily good approximations to their minimum value. So what I want to give you an example of is, what if we take our ideas from the ellipsoid method that we talked about last time, and we talk about looking at the set where X is in some set P, where this set P is convex, maybe might even be some system of linear inequalities. And we also add in the constraint that g of x is at most some value c. So we're looking at all the points that are feasible. They're actually in some convex set P that we care about, maybe some system of linear inequalities. And we also want that the objective value is pretty good because we're trying to minimize it. It's at most c. So just to draw a little geometric picture in here, what if P looks a little something like this, so some system of linear inequalities. And now we also want to draw out something like, the region where X evaluates to, at most, some value C. So whatever that region is, the key point is that we know that that region actually is convex. Because if you actually take any 2 points whose value is at most C, and then you average them and look at G's value at that new averaged point, that'll be at most the average of their values, so it'll be at most C as well. So this is the crucial thing, is that this is why it's important that we'd be talking about minimizing convex functions. What would go wrong if we were trying to maximize convex functions, just to make sure you're on the same page? Yep.
You pretty much want to run as far towards infinity.
You want to run as far towards, exactly. So the set of feasible solutions that obtain at least some objective value is no longer convex. Whereas here, when we put in some constraint that we're looking for feasible points, which also have value at most C, because we're trying to minimize it, then we just get the intersection of 2 convex sets, which now we want to find a point within. And we can do this through the ellipsoid method, because the idea is that every time you query a point, imagine you query a point out here in the ellipsoid method, and we just want to get into the intersection of these 2 regions to find a pretty good point, and then we can do things like binary search over the right C. Well, the issue is that if we query it at some point X, then what should we do if we want to use the ellipsoid method to get into those sets? Too easy a question?
Take both of the separating.
Yeah. All we do is we're going to ask 2 questions. We can look for the separating hyperplane for P. We're already outside of P, so that'll give us a violated inequality in getting into the set. And that'll be the next step that we feed into the ellipsoid algorithm. Or instead, what happens if the ellipsoid algorithm queries some other point X out here? Now this is a little bit more interesting, so what do you think you should do? Any ideas? Yeah?
Gradient?
Yeah. So you have to be, this is why I don't want to get into these technicalities. Technically, you use the subgradient because you don't necessarily know these things are differentiable. But what you're really doing is you look at the minus of the gradient, at least in the case where it's well defined, of this function g of x. That's going to give you some direction that you actually want to move into to get a smaller objective value. And this way, actually, things like the ellipsoid algorithm, even though we talked about it as a way to try and get efficient algorithms for solving linear programs, by virtue of really telling us how for a general convex set, we can leverage separation oracles to get approximately optimizing the objective function, that actually tells us a heck of a lot more than we initially started off with, because it tells us how even to handle fancier things like this. So you remember at the end of class I talked about how we'll eventually talk about things like semi-definite programming. That'll be one other example where we get a lot more out of the ellipsoid algorithm than we were hoping to get when we first started off. This will be one such unit when we talk about how to get efficient things for dealing with submodular functions. And really the main point is we want to develop what this analogy is. The main thing is I want to make good on this claim that a submodular function is the discrete analog of what a convex function is. And that's why the ellipsoid algorithm gives you efficient algorithms for minimizing them. So are there any questions before we actually, yep?
Why can't you just treat your shaded area as the convex region that you're querying over?
Because, well, I'm assuming you're given a separation oracle for P, let's say. You can think about that as a system of linear inequalities. It'll be a very simple system for us, because it'll be the hypercube, the solid cube. But in general, if you had this other function g of x, the way that you could develop a separation oracle for this other set that you're trying to intersect it with, it's just by taking a gradient.
Okay.
Or subgradient, if you will. So this is just intended as a sketch of this idea. But now let's connect submodular functions to convexity. All right, so let's do that. This will take a little bit. Let me use this side.
Quick question. So g of x is the objective, so it's simply a vector or direction, right? So how would it be a convex region? Wouldn't it just be a
as in
hyperplane?
this set x, where g of x is at most c, I claim that that's a convex set because if I took any 2 points x and y, whose value g of x is at most c and g of y is at most c, and then I take those 2 points x and y and average them, that I actually do get something whose objective value is also at most c. That's where you use the definition of the fact that it's a convex function. And that means that the midpoint of that line really is inside a set which has at most that objective value.
Sure, but in the picture, the region would be like the entire hyperplane to the right of.
Oh, so G here is more general than like linear functions.
Yeah.
Oh, we're not doing just a linear.
No. Yeah, it could be like x squared if you want.
Oh, okay.
Or something else like this. It could take an inner product with some vector and then be that quantity squared. So it can be much more general for that, and we'll need that.
Okay.
All right, so without further ado, let me tell you what the connection is between these things. It's through what's called the Lovász extension. So this is a particularly fun topic to teach. It's anything Lovász did is amazing. I think that's fair.
Probably.
Yeah. Never read a bad paper of his. So, here's the main idea. So we're going to take some submodular function, and we start off with this submodular function. I'll always use it as f. We can really think about this submodular function. I know I defined it on sets, a hypercube. After all, we had n elements in the set, so we're just identifying each those sets with binary length little n vectors, so not doing anything fancy yet. But the idea is that what we want to do to actually turn this into a convex function is we want to extend it to actually all of a solid cube. So we want to figure out a way to actually define its values, even when it's not the vertices, the actual points of the hypercube, but anything in the middle, actually in this solid cube. And the amazing thing is that there's a way to do that which actually creates a convex function. So in fact, the way to do it is very simple, but it takes a little bit to show why it works, and it's going to use a very interesting way of actually leveraging linear programming duality and the tools that we've created. So what's called the Lovász extension, I'm going to denote it by f hat, and it maps the solid cube into R in the obvious way. And how it's defined is if you're given some point z in the solid cube, the way that you actually define this is you set it equal to the following expectation. You choose some value lambda, which is uniformly in the interval 0 to 1. And then that in turn allows you to define a set, where the set is you look at all of the indices I, where zi is at least lambda, and you evaluate f, the submodular function, on that set, and you take the average, right? what else would you do? This is basically the most natural thing you could do, right? Yeah? Yep. Is there a question?
Never mind.
Yeah. All right, so it's the most natural thing you could do, and yet we're going to prove some really cool theorems about it. Now, the first thing I want to do is I want to simplify the notation a little bit. Otherwise, it would be a huge headache to carry these things around. So I hope you grant me the following simplifications, which are not really going to change anything. So I'm going to make the following assumptions. So the first thing I'm going to assume is I'm going to assume f of the empty set is 0. Well, you know, I can use what you guys used as your favorite example of a submodular function, a linear function, namely the constant function, and just subtract something from all the values. And it's going to simplify what otherwise would be a little bit notationally cumbersome. The thing which really simplifies the notation is I'm going to assume that this point, z, actually has the property that its coordinates are already in some sorted order. Now, the reason I'm going to do this is because everything I'm going to say would really just apply the same as if you instead took whatever those indices were in the right order. So the first element would be whichever z is the largest and so on. And that doesn't really change things, but I don't want to have to carry around some permutation that maps it into this throughout. So let's just think about what happens to f hat of z when we actually have this kind of sorted order. Now, the first thing that we can do here is we can actually define this expectation in a slightly more convenient way, so having this other representation will be nice. Now, the important thing is which, you know, if I had, this was, you know, true, that whatever point I evaluated at z, its first coordinate is at least the largest, and they were in this sorted order. Now, this expectation chooses a threshold randomly, and then chooses everything to be in the set that's above it. So what I claim is there aren't too many different sets that actually arise in this expectation for this particular point z. So what sets would those be? Too easy? Yep.
Shall we consider taking a very small end and then increasing it?
Yeah.
We're essentially cutting z at some point.
Exactly.
So
right?
you roughly end.
Exactly. This non-uniformity in the values just tells you as you range lambda, right? So at some point when lambda is 1, it's actually going to, you know, if z1 is less than 1, it's going to cut off even this value. And you have the empty set. But as soon as you sweep it downwards into 0, it's taking progressively more and more elements, and it's actually taking them in order. So instead of in some arbitrary order and worrying about that permutation, I'm just going to assume it takes them in order at the point, just to simplify notation. So, you know, what we're going to use throughout is this notion of these sets, which are just the level sets of this. And you could define them more generally for other z's. But in our case, it's just the first I elements. So now what I claim is that another representation of what f hat of z is it's just the following. It's sum from I equals 1 to n minus 1. So n minus 1 here. And what's going to happen is we have the difference of these two values. You know, if the large one minus something that's at least as, you know, is less than or equal to that, that's the probability of actually having a cut point exactly in between them. And in that case, we would actually get the evaluation of f of si. Now we have this other thing that, you know, we also have to add in the probability of getting all of the guys, and that would be zn times f of Sn, which is the entire thing, right? So this is just another representation of what the Lovász extension looks like. So does that make sense? Was there a question? No?
Where does the SI come in from your, what's SI defined as?
SI is the set 1, 2 up to I.
Okay.
So if instead the z's weren't in sorted order already, it would instead be the I largest coordinates. But in our case, to keep things simple, they're just going to be in order, so the first I indices period, because it's in sorted order. Any questions? Yep.
And this works because you're discarding the z1 times f of empty, right?
Yes,
okay.
Exactly. The thing I'm discarding is z1 times f of the 1 minus z1
right.
times f of the empty set, which is 0. So this is the equivalent representation. It would give you another equivalent representation even if you didn't have f of empty set equals 0. All right, any other questions about this? So let's pull apart what the geometric properties are of this. So let me tell you the theorem, which we're going to prove half of, which is anyways the half that we need, and the other half is superfluous to our purposes. And honestly, the thing I don't know how to answer is how Lovász comes up with things like this. Because this was in a time when these techniques were not so common. All right, so one side of this you probably guessed, right? Because I've alluded to it, which is that f, if it was submodular, then this f hat should be convex. Actually, it's even stronger than you think. It turns out that f is convex if and only if f is submodular. Isn't that amazing? So we're going to prove one side of it, because that's the only side we need. The other side is actually probably easier, but we don't need it. So we're going to prove that if f is submodular, then f hat is convex, the Lovász extension.
The other side is possibly a PZ problem also.
Ooh.
Possibly.
No, it can't be because I posted a link to all this stuff.
Okay.
So, and I had to work a little bit to find a good link for it, and the proof in that is very clear. So I know you would give only hundreds on that problem. So let's not do that. All right, so let's prove, one side of this, right? And the proof technique, I promise you, is going to be cool, right? So we're going to prove one side. If f is submodular, then f hat is convex. As I mentioned, we will prove the following, the other direction. Now, this proof is actually, it has a really neat idea, but there's a few things going on in it, so I think at this point it actually makes sense to tell you a little bit about what the architecture of the proof is going to look like, and then the rest of it will just be filling in this architecture. So here's the idea. Here's the sketch of the proof. The main idea we're going to use is we're going to guess a linear program. Okay? We're going to guess an entire linear program, which is going to maximize whatever the z function is. That's what we plug into our Lovász extension f hat. But we're going to guess some linear program on z, which is going to do the following. It's going to have some constraint that x of s, I'll tell you what I mean by this in a second. So x of s is, well, it's a common notation, just to make these things look the same, is that x of s is the sum overall of the indices in the set S of x sub I. And the constraint is that for any set S that's not exactly equal to the entire universe, that x of s is upper bounded by f of s. F of s is something that's exponentially long to even describe, right? So we're writing down an LP that has tons and tons and tons of constraints. We're going to have one more constraint in here, which is that actually in the case of n, we're going to do something special, which is we're going to have equality. So you guess a linear program, and then what else do? You take the dual to this exponentially large linear program that you don't have access to because you don't know all the values of f, right? But the dual is the following, so you can check this. But it's some exponentially large sum, right? Because, well, when you're taking the dual, the constraints, which you have exponentially many of them for all of the different values, those go into the objective function. So you have this incredibly long objective function here, which you can't even write down the values for, but that's fine. And now the constraints you're going to have in here are the following. So you want that for when you sum over all sets S of n, that ys times es I'll tell you what ES is in a second, is equal to the vector Z. After all, the objective function went down into the constraints. Now this set E here is just the indicator for the set S. So it has a 0 outside of S and it has 1s in the set S. And whatever Y values you plug in has to have the property that it exactly recovers Z. And now you have some constraints on the YS's, is that YS needs to be non-negative, but only for sets S, which are not the entire universe. The reason that you don't have a non-negativity constraint on the actual set, which is the entire universe, so can anyone tell me why that is? Just as a quick check about understanding duality. This is hard though, so if you get this, you know, why is this why don't we need a non-negativity constraint on n? Yeah.
You have the equality.
Perfect. Exactly, right? It's because you remember that for things like weak duality, when you have an equality, then you can actually multiply that equality by a positive or negative thing. And because it's an equality, you don't have to worry about the sign flipping. All the other things are inequalities, that's why you need them to be non-negative. So even for things, especially for things like this, where they're extremely, you know, long, LPs are difficult to wrap your head around. That's why it's important to understand the rules of duality here. So let me tell you the key lemma. From all of this, everything else will fall. So here's the, you know, brilliant idea. Well, this LP actually has a lot to do with the Lovász extension. If you plug in Z as the objective function, and you solve this LP to optimality, the primal, the optimal value would be the Lovász extension. So that's the magic, is that this LP actually captures exactly what f hat of Z is. So this is the step from which everything else follows. So this should actually surprise you. You know, what should this have to do with f hat of Z? Now what I claim is that we can now at least modulo this lemma finish the rest of the proof. So why, if we had this lemma, would we actually know that f hat now actually is convex? So the idea here is that f hat of, let's just plug in, you know, two different values Z and Z prime. Or you can think about taking their average. Maybe let's do that. So let's put in a 1/2 in front of these guys. Well, that actually, we know through this lemma, is the same thing as the max over X, which is feasible for this primal P of 1/2 Z plus 1/2 Z prime transpose times X, right? And now this guy, well, you can do only better if you were allowed to take the max over these two things separately, right? So you get that it's upper bounded by 1/2 times the max over X is feasible of Z transpose X plus 1/2 times the max over X is feasible, and you can choose different X's for these two maximizations. That's the important thing. And now this quantity right here is just 1/2 times f hat of Z. And this guy is 1/2 times f hat of Z prime. Right? So does that make sense? Are there any questions about this? Does this look mysterious? Very mysterious? Because this one lemma is hiding the entire, you know, issue, right? So, any questions about how this would finish the argument? Yep.
Can we go back a couple steps?
Yep.
What is ES?
ES is the indicator for some set S. So if you think about S as being just the first element, then it's the vector 1 and all zeros. If the set S is the first two elements, it's 1, 1, and all zeros.
E is a vector. ES is a vector for
ES is a vector.
S.
Okay.
Of length, little n.
And what is YS?
YS is a variable.
Which is also a vector?
No. It's just a real, I mean, it's a non-negative value.
Okay.
So this gives me exponentially many vectors. One is the indicator function of every different set. And I want that the linear coefficients I get when I add them up exactly recover z. Z is a length n vector because it's an inner product with x.
Okay. And then going up one line, what is that summation over?
Oh, sorry.
Okay.
Make sense? This is a little bit abstract, but this is how we're going to do it. Are there any other questions to this? Yeah?
That symbol with, in the last line between S and N, that's just proper subset.
Yeah, so just not equal to n. Yeah, exactly. Proper subset. That's because we don't need a non-negativity constraint for y sub n, because up here it has an equality as the constraint. Any other questions? All right, let's move on to the magic. So does anyone have any ideas about how to go about proving the lemma, which I agree carries the heart of the issue in there? So we already guessed an LP. Why not guess its optimal solutions? That's what we're going to do. So that's the pattern he took. Guess two LPs if you're exponentially large, and then guess their optimal solutions. Why not? Let's do that. So this is, we went through like the ellipsoid method, right? Which that gave you an algorithm for actually computing the optimal value to an LP, at least of its polynomial size. And here we have an exponentially large LP. And, so ordinary people need the ellipsoid method to solve LPs. I think Lovász just guesses the answer. So the complexity might be O of 1. I'm not sure. But in any case, he solved it. So here's how you do it. So you set xi star, this will be the optimal solution, to be f of si minus f of si minus 1. Remember that si is just the first I element, and in general, if the zi's weren't in sorted order, it would be something else. And the same way, this is the first I minus 1 element. And we're going to guess this solution, and what we're going to do for y is we're going to choose ys star is equal to, well, we're only going to use a small number of values for this optimal solution. That's actually part of the main insight, is that if the set S is equal to Si, what we're going to do is we're actually going to look at the difference of these two values. This is something non-negative because the zi's were in sorted order to begin with. We're going to set it to be equal to Zn if S equals n, and we're going to set it to be 0 otherwise. So this is the pair of solutions that we want to work with. Now, what I claim, we'll work up towards proving the lemma in a few steps. So claim number 1 is I claim that y star is feasible. So can you guys help me out with that? This is actually the easy one. I'll do the other one. Y star is feasible, the choice of these y's. Yep.
And so, first of all, you're no longer summing over 2 to the n steps, you're summing over only these n.
Yes.
So you have the Zn times 1, 1, 1 all the way, and then Zn minus 1 minus Zn times...
Yes, exactly. Exactly. So let me write that up on the board now. That's exactly the proof. Now the first statement is just that it's obvious that this guy is certainly non-negative just by our choice of that these things are in sorted order. In fact, even the nth guy is non-negative, so that's a little bit of an accident. But here's the idea for the proof. So as I said, because these guys are in sorted order, this implies ys star is non-negative everywhere. And the key point is that if you look at this sum in this left-hand side right here, the sum over all sets S, then you look at ys star and es, where es is this indicator function of the ith set. What if I take this length n vector and I look at its ith coordinate? Then all I'm doing, I claim, is I'm adding up a bunch of different values of y star. Because when I look at the ith coordinate, well, the first ys1 doesn't contribute because it only has a 1 in the first coordinate times some coefficients. And it's only when I get out to containing the first I elements that I actually get a contribution from each of the different y's. And then after that point, I keep getting contributions. So does this make sense? Everyone following this? Yep. So now, this thing, if we just look at it, well, I mean, we have, we get a lot of cancellations here because we have a telescoping sum. And lo and behold, we get zi. And that implies that actually when we take this vector right here and look at its ith coordinate, we get the ith coordinate of the right-hand side, and that works for all of the different coordinates, so we're done, right? So this guy is actually feasible. That's the first part of the proof. Now we're going to show the other parts of it. So let's see, how do I want to do this? All right. Good. I said I'd do the work for this, right? But I lied. As in, I'm going to do it later. So this is actually a little bit more work than, claim 1 was very easy. This is going to be a little bit, but not too much. So what I want to do first is I want to defer this so that we see the overall architecture of the proof. And then we'll see, given these two things are good, how we can actually fill in the proof, and then we'll go back to finishing this claim. So I lied, but that's all right. So what I now want to do is, what should we do to actually complete the proof? If we had claim 1 and claim 2, what's the remaining thing that we need to check?
They're equal.
That they're equal, right? That's it. So just to make sure you guys are on the same page for actually finishing the proof, right? So here's how we would finish the proof. Well, all we have to do here is we just have to write it out. So z transpose times x star. Well, writing out what this literally is the sum over I in n of zi. So it's a length, n vector times itself f of si minus f of si minus 1, because that's how we set x star to be equal to. So what else would we do here, right? But now the important thing is that if you look at the coefficient of f of si, then it actually gets contributed to twice, because once it plays this role, and once it plays the other role. So let's write it out in a slightly more convenient form, which is the other way of writing this out and reworking this sum, is we can instead think about grouping together the contributions of the different f of si's together. And lo and behold, we have this remaining term f of sn that actually doesn't play two roles in here, because it only appears once on the positive side. So this now is exactly what?
Y star.
Y star times.
Yeah.
Sure, yeah, you guys are, yeah, let me, so I just mean, first of all, this is our other definition of the Lovász extension, f hat of z. And then this is actually literally just from looking at this thing. It's the same thing as summation subsets of s, ys star, f of s. Because we only have these types of si's actually showing up. So this actually would be an optimal solution for this, right? That their objective values are equal and they're both feasible, modulo this claim number 2. So now let me prove for you claim number 2, and then we can actually call it a day a little early before spring break. Are there any questions before we do proof of claim 2? Yep.
Are we ignoring the non-ordered case, or what's
The what?
the case where the z's aren't ordered?
Oh, so what I claim is that this entire proof works verbatim if the z's weren't ordered. It's just that what your notion of SI is would actually change. So instead of it actually being elements 1 through I, because those are the I largest, it would be whatever the I largest are, and you can break pi's arbitrarily as long as you do it consistently. So what I claim is that this entire proof, if you were to throw in permutations everywhere, which I think would be a little bit of a headache and would obfuscate some of what's going on, would actually work verbatim. But that's a good question. Are there any other questions before we prove claim 2? Yep.
Might be some question, but what's going on bottom right in the middle of the board? What's the E of S is the indicator variable?
So this is a vector,
Right.
and I'm taking the ith coefficient of it. Because see, I want to prove that this vector is equal to the z vector. So the easiest way to do that is actually just to check it on a coordinate by coordinate basis.
Why is it a vector?
So this, see if you look up here, right? So ES is a vector, YS is a scalar. ES is a vector of length little n, and Z is a vector of length little n. So when I actually am checking this equality, that this vector equality holds, then what I'm doing is I'm taking the left-hand side and I'm looking at its ith coordinate of that vector, and I'm taking the right-hand side and I'm looking at its ith coordinate, and I'm proving that they're equal, and that proof works for all I, so hence the two vectors are actually equal, which means that it's actually feasible. Good. Any other questions? Yes. All right, so let's prove claim number 2. So what I'm going to do, we want to prove that X star really is feasible for this guessed solution that we've created. So what I claim is that, so there are a few things to check. One is really trivial. So, what I claim is clearly X star of n equals f of n. So remember, X star of n is just taking the value of X star on all of the different coordinates and adding them up. And then we get exactly the same telescoping thing, and all we're left with is the f of Sn, because it's defined differently there, right? So we get exactly the same telescoping sum, and so this part clearly holds, that's the easy part. The more interesting part is actually showing that the inequalities hold for every set x, that x of s is at most f of s. So we're going to prove the remainder by, we're going to prove rest by induction. And we're going to prove it by induction on the size of whatever set S that we care about. What I claim is that for S is the empty set, then what's X of the empty set? Just using the definition of X? Zero, right? Because X of S is just adding up all of the coordinates in X. Sorry, this should be X star, but it doesn't matter. It's 0, because we're adding up all the coordinates in the empty set, which is 0. And this is definitely equal to f of the empty set, which was one of our assumptions, that f of the empty set is 0. So it's clearly true on size 0 sets. Let's prove the rest by induction on S. So what I claim is that we're going to start off with some set x, right, which we haven't proven this claim up to that size. And what I'm going to do is I'm going to let I be the largest element in X. See, we have these easy sets, which are the prefixes, right? We have SI as the first I elements. Well, S here could be arbitrary because we have exponentially many constraints, one for every set. All I'm going to do is whatever your set is, tell me what the largest element is. That's the last element to be added when you actually start looking at these thresholds into the set. So let I be the largest element in the set. And now what I claim is that, well, we certainly have the following property, that if we take the set Si minus 1, the first I minus 1 elements, we take S, well, this better be an upper bound for f of S union S I minus 1 plus f of S cap Si minus 1. Why is that?
Submodular.
It's submodular, right? That was our other definition of submodular that you're going to finish the proof for, that those two things are equivalent. Now, let's try and make things a little bit simpler. So I claim 3 of these sets have just more convenient names. I can't really simplify this, it's S. So this is, the same thing. We already know that this guy is 1 through I minus 1, right? That was our definition of it. What I claim is that S union Si minus 1 also has a nice name. What would that set be? Si. Exactly, right? Because Si minus 1 contains all the guys up to I minus 1, and I is the last element in S, so that actually gives you Si for this. Perfect. And what is this set?
S without I.
Yes. It is S without I, right? Because you have to have everything in S, but the thing that this guy kills is the ith guy. Yeah?
I'm confused about S. What's the difference between S and S sub I?
S is an arbitrary set.
Okay. And what about SI?
SI is actually this level set. So if you want, I can change the notation to make this a little bit more obvious. I'm not sure this will help, but I'll try. So we can think about an arbitrary set T. T has nothing to do.
SI is defined on the upper right board.
Yeah. SI are these level sets from 1 to I.
Got it. Okay.
Good. So T here is a completely arbitrary set, right? And we're actually doing induction on the size of T. Okay? And these are the different sets that we get out from doing this. This way the S and the SI is not as confusing. So now let's rearrange. Right? So what I claim is by rearranging, we actually get f of t. I'm going to keep this guy over here. I'm going to pull this guy over to the other side. But in fact, I'm going to group it with this term. So I'm going to get f of si minus f of si minus 1, because I pulled that guy over. And then I'm going to get f of t minus I. So what's this?
XI.
Perfect. Xi star. And the hardest part about that is getting the stars right? And what can we say about this guy?
By the inductive hypothesis.
Yes.
Greater than x of that thing.
Yes, exactly. It's at least x star of s minus I.
T minus.
Oh, sorry. This is the problem with changing your sets on the fly. It's t minus I. Now we're done, right? Because the entire thing is then less than or equal to x star of t. As we're adding it up on all of the elements in t except for I, and then we add back in I. And now we're done. That's it. So I promised you this would be a little bit easier, but since we do have a couple minutes, let me just refresh your memory about this is a very interesting architecture for a proof. That this is a completely different way of using LP duality. We started off with a function f, which we have only black box access to, right? And it has the submodularity property. It's not at all obvious that you can try and minimize any such function, right? Even if you were given a lot of query access to it to begin with. So if you think about some of the submodular functions that we talked about, like the coverage function, right? Well then, that function was actually defined by bipartite graphs. So I could just write down the bipartite graph, and we all know P equals NP, so then I could just solve the problem. Oh, sorry, all right. Well, we could run an exponential time, we could solve it, but here what's not so clear is that you can actually do this problem with making only polynomially many queries to the function to begin with, which is exactly what happened. So we had a function that was defined on exponentially many things, and it really does have exponential description length. And yet, lo and behold, the idea was that actually even discrete notions can have continuous undercomponents to them. So a lot of Lovász's early great ideas were about connecting things that were only about discrete optimization to purely continuous problems, to polytopes and to LP duality. That's exactly what happened here, is that we had this discrete function, the submodular function, that turned out to have an extension that actually is convex in a geometric sense. And how do we prove it was convex? We actually guessed an LP, which the optimal value for the LP is itself the Lovász extension. And we proved that fact by actually guessing the optimal solution to the LP and showing that the primal equals the dual for that pair, and actually equals the thing we wanted it to be equal to, which was the Lovász extension. So I think this is a really beautiful proof of the way that LP duality can be used in very surprising ways to prove facts that at first glance have nothing to do with it. So we'll stop there. I hope you guys have a good spring break. And then one of these fine gentlemen will be teaching you on Monday. And I'll see you on Wednesday.